All right, cool. Focus. Okay. So let's see. Yesterday we did this side. Look at all that stuff we did. That's crazy. And then we got a little bit on this side. And I'm going to take a step back and talk about a larger idea, and then we're going to come back and finish this guy up. Everybody's got this guy. It's on the other side of the 10-2. Does everybody have this? All right. So you guys help me out. So I'm not sure what is 3 times 7? That's crazy. Why are we allowed to multiply those? Because they have the same root. So if I had the square root of 3 times the square root of 7, that would be so the no root of 3 times the no root of 7 is the no root of 21. The square root of 3 times the square root of 7 is the square root of 21. If you want to see something a little more proofy, right, just to make up a word, somebody help me out. Now I'm going to show you why this is true, and then we don't have to worry about it anymore. How do I rewrite the square root of 3 with a fractional power? 3 to the half. And then how do I rewrite the square root of 7? Half. That's crazy, man. Now watch this. Now, it looks like somebody distributed a 1/2 power. So I can undistribute it like this. Do you guys see that step? What would I do that 1/2 power? I could distribute it in. Well, if it's to both, I can undistribute it. And I'll show you something interesting about what I just said in a minute, but you'd all know if I had a little side note, appropriately enough it's on the side. If I had 2a squared to the 3rd power, what would that be? How do I simplify this? Yeah, 2 cubed is 8. A to the 6th. So here, I could take a cube out if I wanted to. So here, I'm just taking the 1/2 power out. And what is 3 times 7? Still 21 to the 1/2. And how do I rewrite 21 to the 1/2? That is the square root of 21. I like it. So why do all this shit? Just say, oh, as long as they're the same root. If they're the same root, these are the same, and I can take it out. If they're not the same root, if one of them was a cube root and the other one was a square root, that'd be a 1/3 and a 1/2. They're not the same. I can't take them out. So as long as they're the same root, I'm allowed to multiply the insides together. Same thing we've been doing forever. You just didn't realize. But if they have no root, I'm allowed to multiply together. It's the same root. So what is the... so this is all you got to do right there. You don't have to do any of this. This is just me showing you why it works. So what is the 5th root of 2 times the 5th root of 7? Fifth root of 14. There's too much thinking happening, which is weird to hear teachers say, but yeah, you guys are thinking too much at the moment. 5th root of 2 times the 5th root of 7 is the 5th root of 14. Is that cool? What about the cube root of 5 times the 4th root of 2? What did we just say? Why was this one so easy? Because they are the same. This one's actually really easy too, because they're different. Can I do anything? No. So already simplified. the problem could say plug these in your calculator, get a decimal, but by hand, I can't do shit. How are we feeling so far? Let me stop right here. Is that decent, you guys? Okay, I'm going to go off the 3 people that said yes. I'm going to tell like this, everybody. Okay. So, notice something else too. Now, let me see if you guys get this. So, the roots have to be the same if I want to directly multiply the insides. Well, what is it about exponents that allow me to multiply certain things? As long as the base is the same, I could do something, right? So what about if I had, instead of this, if I had the cube root of x times the 4th root of x? Now, believe it or not, there is something you can do, but can I just make it x squared inside? Why can't I do that? Because Jeff waves his arm. Because what? The roots are not the same. I like it. I keep thinking the root's the band. But how do I rewrite the cube root of x to the 1/3? How do we write the 4th root of x? They're the same base, so the properties of exponents say I can just add the powers together. How do I add those powers together? What do I need? Like denominators. So it'll be x to the 4/12 plus 3/12. So x to the... Now I want you to... So again, if the bases aren't the same, I can only multiply them if the roots are the same. Something somewhere's got to be the same, right? If the bases are the same, I want you to realize why we're able to do something. From this step to this step, what did the root become? It was a cube root and a 4th root. Well, now it's a 12th and a 12th. I've made the roots the same. That's why I was able to do something. I love that idea. You can only multiply them if the roots are the same. But if the bases are the same, I can then do this and make the roots the same. Aren't they now the 12th roots? What is x to the 1/3? What root is that? What? Cube root. X to the 4/12. What's the root? No. What's the root? Where are roots? On the bottom. 12th root. So x to the 4/12 is a 12th root. X to the 3/12 is a 12th root. So when I make an LCD, I'm making the root the same. Because where are the roots in fractional powers? They are on the bottom. So it's a really cool idea. If I make the bottoms the same, I'm making the roots the same. So that's kind of nifty. Did you have to look at it that way to be able to do this? No. So why are you messing us up, Jeff? No, it's a beautiful idea. I want to point it out. So if the roots are the same, you can multiply them. If the bases are the same, you can at least do this. If neither the roots or the bases, screw it. You can't do shit. Forget it. Just say already simplify. So this is why this idea right here, if the roots are the same, I can multiply them together. Well, then I can do the opposite. I can tear them apart, right? You're tearing me apart. It's a good movie. Needs to be. Watch it. So we did this kind of thing yesterday, but let me try to do this again with you guys. The square root of, let's make something up here. Yeah, I like it. Square root of 52. Does anybody know what the square root of 52 is? No, stop doing your calculator. That would mean your calculator knows what it is, you don't. So stop. Can somebody tell me what it's a little bit more than? 7. It's a little more than 7 because the square root of 49 is 7. So if you had to estimate, you'd say a little more than 7. But I want to know what it is exactly, which means I got to be able to break this thing apart. So how can I rewrite 52 as a product of two things where one of them is square rootable? What goes into 52? Say again? No. All right, I'm going to address that thing in a minute. You've got to break it up multiplicatively. You've got to break it up multiplicatively. The square root cannot handle sums inside. It can't go across a sum. Say again? So what the hell do you do in general for these guys? Stay with me. Real quick, side notes. If I have the square root of 9 times 7, I can do something to that. I can break them up. I'm like, what fool put these together? Maybe make the square root of 9 times the square root of 7. Right? Undoing the multiplication. They have the same roots. I'm just going to pull them back apart the way that I put them together earlier. What's the square root of 9? 3. What's the square root of 7? I don't freaking know. So what I'm trying to do is rewrite this to look like this. So what do you try to divide 52 by? Squares. 52 divided by 4 works. Holy shit. Right? 52 divided by 4 is 13. Now what do I do with this? Break it up. Square root of 4 is 2. Square root of 13 is, I don't know, third base. So we'll have it custom. Do you guys see this? So the thing that we just barely got into yesterday is related to the fact that I'm allowed to multiply like roots. I can multiply the insides, so I can tear them back apart if I want to. I don't know, guys. Okay. Now, real quick, I want to address something that came up earlier in lab, and it kind of came up just a minute ago. Now, watch this. Who can tell me what are coefficients based on? They are not based on multiplication. Don't say, well, it's 3 times x. No, what does that 3 mean? There are 3 what's doing what? 3 x's doing what? To each other. Adding. So coefficients are based on addition, right? Right? Yes. Okay. So we get x plus x plus x. That's amazing. That is why this is so freaking easy. Because coefficients are based on addition, they play well with addition. How does this work? No, even more directly. I like it. I'm not proving the distributive property. I'm just saying. The reason that works so nicely is because coefficients are based on the operation that's on the inside. All right, now watch. What are exponents based on? Multiplication. So what are they going to play well with? When there is multiplication on the inside. That's easy. What did I do here? Distributed. The 3 times this. The 3 times this. What do I do here? Distribute. The to the third. The to the third. I distribute that. What's 2 to the third? 8. What's x to the third? You just said it, Jeff. Okay. So, what the shit is this? It is definitely not distribute the 3 because exponents are not based on addition. They will not play well. I don't know if you can understand. I love that phrase. They don't play well with addition. What would you have to do this? You have to work your way around and get all these frickin' terms just because you've got 2 operations that don't play well together. So you got to kind of get around it somehow. So, let's bring it back to what we're dealing with now. What's a way to rewrite, there's a problem that sort of looks like this. What's a way to rewrite square root of x squared plus 16? How could I rewrite that? Stop trying to factor that because it's the sum of squares. It's going to make me cry a little bit. Can't factor that shit, right? It's the sum of squares. Cannot be factored. But I can rewrite a square root as a 1/2 power. Can I distribute that? We just talked about it, right? Please say yes. You say no. Good. Because it's addition. That is an exponent. They are different operations. Therefore, they can't. Exponents are not based on this. So you cannot just say that this is x plus 4. No. 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 You can't distribute a square root across addition or subtraction because they're not based on the same thing. This is the kind of thing, and don't take what I'm about to say to mean that I'm going to be lenient on you if you make this mistake. I will not be. So I don't want you to get to Math 285. Yeah, I'm calling you guys out if you ever watch this one. And they do this shit all the time. That's Math 285. You want to watch me cry, you just watch me grade some of that shit. I mean, seriously, this is where you learn this and you never do this. When you get to 285, that should just be a part of your DNA. And you're doing this shit, make me cry. All right, does that make sense? Your brain wants to do something to this. Your brain's like, x squared 16, oh my god. But then you got to go, no, brain, that's addition, can't do shit. Okay, is that? But what could I do with this? Factor it. Because if I can make the inside some kind of multiplication, then maybe the root could do something. And sure enough, this factors to be x minus 4 squared. So what happens there? Yeah. This is almost right. Because I didn't say the inside can't be negative number. All right, I like it. But basically the idea is I rewrote the subtraction addition problem in terms of multiplication, and roots are powers. It plays well with multiplication. Okay. All right, that's enough side notes for right now. Let's come back to, not this guy. Let's come back to this guy here. Now, this is that 10-3 handout. Everybody's got this, right? I think a few more people came in. Everybody's got this one? Okay. Okay. So I give you two methods. I'm going to kind of do this method more often when I'm talking about it because this method is a little bit better. But if you like this method better, that's fine. Just do it correctly. It's just easier to make mistakes with this method. That's why I try to get you to do this one. Let's do one more together, and then I'm going to unleash you on the rest of them if you haven't done that yet. Got a lot of time left. So see how we did this one yesterday? We broke it up into a square times something. So what do you think about 72? Beautiful, I'm going to do it. 9 times 8. You guys see that? Is that cool? Square root of 9 times 8. Why is that a decent choice? Maybe not the best choice, but we're going to see that in a minute. Why is that a decent choice? Because 9 is square root of it. So this is square root of 9 times square root of 8. What's square root of 9? 3. Now, what's kind of wrong with this is, what does 8 have in it? A 4. But it's just like reducing a fraction. You might have to do several steps, no big deal. What is the only operation in there right now? The 3 and the square root of 8, what are they doing to each other? Multiplying. So anything else I take out, anything else I square root, is going to multiply by that 3 because it's all multiplication right now. How do I break up 8? 4, 2. And what's the square root of 4? Times 3?
6.
So Mark had a good idea. He said, well, why don't I just make this square root of 36 times 2? Because 36 times 2 is 72. And what's the square root of 36? 6. What's the square root of 2? I'm the same answer, of course. That's like simplifying a fraction in one step or simplifying it in 2 steps. Who cares? You just do it the way you see it. And again, to remind you guys, this is sort of a version of mixed numbers. I got a whole number and a radical number, right? All right, you guys keep going. Do the next few, and then I'll catch up to you if you haven't already done those. If you have already done those, maybe help somebody near you. Oh. Did you not get one of those? Oh, sure. Asia, are you out there? Asia? Asia.
I already finished it.
Oh, cool. We'll just hang out for a little bit.
The other 10.3.
Did you get this one? I mean, it's on the other side of the 10.2. No?
Not Amazon.
Okay. So when you're not sure, you could divide 120 by 2 and 3 and 4 and 5 and 6 and whatever, but it's a little bit smarter to divide it by 4. If that doesn't work, divide it by 9. If that doesn't work, divide it by 16 and 25. Because you're trying to break it up into a square number and something else. So be smart about what you're trying to divide it by. Just like reducing fractions, sometimes you cannot reduce it. So sometimes you cannot simplify. So maybe one of these is already simplified. Now, let me try to catch up to you guys. How do you break up 120? 30 and 4. Like square root of 4 times square root of 30. Bless you. Square root of 4 is 0. Square root of 30, I don't know. And 30 is 2 times 15, which is 2 times 3 times 5. And I know I can't do anything with it because I don't see anything that happens twice. You guys see that? 30 has nothing in it that happens twice. 30 has no squares in it. So I stop. What about this guy? You can do 4 and 20. Well, what's 20 have in it? Another 4. So you can do 16 and 5. Now again, if you did 4 times 20, you could do it, and then you have to break 20 up again and do it. That'll still work. But here, what's the square root of 16? 4. Square root of 5? I don't freaking know. And again, I really want to remind you, because this is such a beautiful analogy between these analogies. If I had 21 divided by 5, I could break that up into a piece I can do and a piece I can't do, which is basically what we do with this. So what's 20 divided by 5? 4. What's 1 divided by 5? I don't know. I mean, it's the same thing. It's the same beautiful thing. Division cuts addition down. Square roots cuts multiplication down. It's the same kind of thing, just on a different level in the order of operation. I don't know if that helps. I just like to say it. What about this guy? Yeah, he doesn't have, he's got 3 and 11. Does he have 2 of anything? No, so he's done. Right? He came in the door done. Done on arrival. What's up? Could have been a good joke, I don't know. Alright. Do these. So what do you think about cube roots? Same idea. You try to break it up into a cube number. What are cube numbers? 1. No. 8. Why is 8 a cube number? Because 8 is 2 cubed. 27. 64. 125. That's plenty. Yes?
Could you do the cube roots with the second method too?
Yeah. And then you look for groups of 3. So you can break the number all the way down, the second method that's up there, And then you look for groups. Every group of 3, you see one of those comes out. Right. Okay. Oh, let's see. Maybe I should do one the other way too, yeah. Okay. Yeah, that's right. And one of these is just doable. Here, what's the cube root of 64? Done, right? Just like if I said, make 14 over 7 into a mixed number, you'd be like, I can't, it's just 2. All right. There's no extra piece, it's just 2. Here, there's no extra shit inside, it's just 4. That's the answer. Takes 3 fours to make 64, done. What about this guy? How do you break him up?
8 times.
Yeah, so this would be cube root of 8 times the cube root of 5. Cube root of 8 is 2. Cube root of 5 is, I don't know. I'm going to do a couple of these I'm going to do it with the second method just to show you how it looks, if you like that method better. And what about this guy?
9 times 6.
And what's not good about, I'm not saying you're a bad person, but what's not good about 9 and 6? Are either one of them cube rootable? No. 27. And see, 9 times 6, doesn't 6 have a 3 and a 2 in it? 9 times 3 is 27, so 54 is 27 times 2. I can recombine the DNA of the problem. So I get cube root of 27 times cube root of 2. Cube root of 27 is 3. Cube root of 2 is? I don't know. Let me show you a couple of these, the other method, just to show you what it looks like. Let's do that cube root of 40 problem using the other method. So if I just break 40 down, just break it down, break it down, break it down. Is that cool? What do you see 3 of? 2's. So on the outside I put a 2. And this poor little dude, there wasn't enough for him to break out. So I'm trying to come up with a way. One of my colleagues teaches this to be like a cube root prison. And it takes 3 of the same thing to break out. But what's weird to me is like 2 of them die on the way out. And it's a little, I'm pretty morbid because I'm killing everything, but still, it's a little bit, go on without me. Sure thing, no problem. Anyway, so we'll see if that ever comes out to be something. Is that cool that you guys can do this way? But again, that mistake I always see is these end up in the wrong place for some damn reason. All right, okay. What about number 9 there? Yeah, it's kind of in your face there. 8 times 111. What's the cube root of 8? 2. Cube root of 111? I don't know. What number goes into 111?
37 and 3.
Yeah, 3 goes in. How would I know 3 goes in? Because 1 plus 1 plus 1 is 3. But it's 3 times 37. 37's prime. 111 ain't going to go anywhere. So I stop. Always so hopeful. Do my hopeful Tai Chi. Yep. And then finally, what about this dude? What's 100 got in it? 10 times 10. So does it have enough? This is 2 times 5 times 2 times 5. Do I see 3 anything? No. I'm done. The only way you can do the cubed as some number is if it has 3 of the same factor in it. The only way to do a square root of a number if it has 2 of the same factor in it. If it doesn't, I can't do it. Okay, I like it, I like it, I like it. I like it a lot. Okay. Sweet. So, let me show you, well, first thing I'll show you is this. Boom, boom, boom. Boom, boom. So in lab next Wednesday and Thursday, right before I lose you for the break, I'm going to quiz the shit out of you. So it's on the first 3 sections of... What?
Planning on it, but I guess now we're getting
Don't quit me. I can't quit you. All right. Well, yes.
When I read it, at first I thought you said quit. I didn't get it.
Oh, yeah.
I was like, what? I'm going to quit.
Okay.
Oh, man.
All right, we're out of here.
I love it. You guys are gonna be like, my math teacher's giving me subliminal messages. Give up. You ever seen Labyrinth? Turn back. This is not the right way to do this problem. No? See Labyrinth. He's bored. David Bowie. Shit. Alright. I want to show you an immediate use of what we just did. I'm kind of jumping ahead a section or two. I can't remember. And I don't care. I want to show you something coming up. And it shows you why we try to reduce radicals. That's what I call simplifying radicals. I call it reducing. Tell me what this is. What is x plus 2x? 3x. Look. You know, like, is there a trick? So, and why is that 3x? Because I got something I don't know plus 2 more of that same thing. So I got 3 of those things I don't know, right? So what's the square root of 7 plus 2 square root of 7?
3 squared.
There we go. I got one of them here plus 2 more of the shit that I don't know. So I got 3 things I don't know. Do you guys see that? What do coefficients do? They collect like terms. They collect things that I don't know. So that's why variables work this way. Do you know what square root of 7 is? No. I got 2 more of them. Oh, shit. I got 3 of these weird-ass things. Right? I like it. Might as well just quit. No. All right. So what about... So that's nice. That's nice. So what do you think about this? 2 square root of 3 plus square root of 12. Can you add those like that? No, because they had 2 of one thing plus something else. But what can you do with this? Yeah. You can break 12 up as, what's the square root of 4? 2. What's the square root of 3? I don't know. And that is? 4 squared. So if this would have been like 2x plus y, is there anything you can do? No. But these, they're not really like x and y. They are numbers. Sometimes I can work with them. So that's why if they start off not like, maybe I could do something. Because they're not variables. They are known things. They're just ugly numbers I don't want to look at. But I could do something sometimes to make them like terms. Right? Okay, good. I just want to show you that. I think that's 2 sections in our future. So here's the last thing we'll talk about today. We're going to get into it right now. I love you guys. Like 15 minutes ago, everybody's looking at the clock. Really? Shit. Yes?
Okay, so you were saying that the square root inside is compared to the base of a fraction? the same
Yeah,
number?
yeah. So if I had 2/3 plus 4/9, are those like terms? No, but again, they are numbers, just like these are numbers. Maybe I can do something about it, and of course, what do we do about it here? We multiply this by 3 on top and bottom. Yeah, so it's similar. I like it. It's that idea of like terms. Can I do something to make it like? If it's this, no, I can't do anything. If it's this or this, maybe I can do something. Because they are numbers, maybe I can do something. Okay, cool. I like it. Okay, here's the last thing for today. Do I have any paper left? Sort of. Shice up. Whoa, what just happened? Did it get brighter in here? Ghosts. It's evidence of ghosts. There it is. Good ghost hunters out here. They could run around for a bit. Let's get the Bigfoot people out here too. They could run around, not find shit. All right. So what did we just talk about? We just talked about multiplying radicals. So what the hell are we going to talk about now? Dividing radicals. So let's start off with something that should be obvious based on what we just did. What can I do with this? I'm not going to turn those lights out, by the way. If that ghost wants them on, I'm not going to mess with it. You should, yeah. All right. What can I do with this? Are they the same root? They're not the same root.
Yeah, same.
They're the same root. So am I, just like when they're multiplying, if they're the same root, I'm allowed to multiply them. Division is multiplication. So I better, if they're the same root, I better be able to divide them. What is 98 divided by 2? And let me show you a little interesting way to do this. There's two square roots. Let me make one big-ass square root. That's another way to think about this. You don't have to think about it this way, but... And now I get square root of 49. You can just go straight from here to there if you want to. And the square root of 49 is 7. All right. So you can multiply or divide if the roots are the same. I like it. Oh. So let me give you one more of these. And then I'll see if I can't talk about something else without you rebelling. So what if I had cube root of, I don't know, 56 divided by the cube root of 7. Yeah, 56 divided by 7 is 8, and the cube root of 8 is 2. All right, one more like this. What about the 5th root of x squared divided by the 7th root of x to the 5th? Do that. Are they the same root? No, shit. But they are the same base. All right, so you could do something. In theory. If you look back at our multiplication notes a minute ago, we had two that were the same base but not the same root. You probably do the exact same thing. which is what I do here. X to the, power is 2, root is 5. On the bottom is x to the 5/7. And then what do I do with those? Yeah. I'm going to do what with the fractions? Subtract them. There it is. So x to the 2/5 minus 5/7. Why do I subtract them? Because that's what I do with like base powers when I divide them. Always. I don't care that they're fractions. I don't care. So the LCD, of course, is 35. This will be 14. This will be 25. So I get x to the negative 11 over
35.
Which is
Root 35.
nah there. Yeah, you're right. I mean, we started with roots. What would that look like as a root? This would be 1 over as a root. What's the root?
35.
35. 35th root of x to the 11. Kick ass. Okay. So here's the real last topic of the day. Do this without. Okay, you guys are okay with it. Cool. And this is something I sort of hinted at before. What's the cube root of a cubed? A. So what's the cube root of a to the 4th? This is what you were talking about earlier, Mark. We're finally catching up. Watch. Now I'm going to do this a certain way that you can do it, but I'm going to try to show you you desperately do not have to do it this way. It's going to explain why my little shortcut works. I can do this the same way we did numbers. Like if I had the square root of 50, I can't do that shit, but I can break them up. So a4, I can break it up as a cubed times a. There's one extra a that somebody threw in there, right? So I can break it up. What's the cube root of a cubed? A. And what's the cube root of a? I don't freaking know, right? So you can make it work the same way. But since roots are bottoms of fractions, I can actually do this fantastically beautiful thing. 3 goes into 4 once with 1 left. In this case, left inside. Right? So there's a beautiful shortcut there. Why does it work? Because roots are bottoms of fractions, right? When you write it in power form. So let's do another one. What if I had the 5th root of b to the, what you got there? 17. 5 goes into 17 3 times with 2 left over. Done. Almost too nice to believe. But again, the other way to look at this is if I wrote this as b15 times b2, do you see why there's 2 b's left? Because there are 2 extra b's. And what does extra really mean when you divide? It's remainder. That's the extra shit. That's why division works also. And because they're fractions when you rewrite them. So of course division works, because that's what they really are. Oh, you guys like this one. All right. Here we go. Let's do it. This is the last problem, okay? No lies. I didn't lie earlier. I just was not really paying attention to myself. What is the 4th root of, look how long I made that shit. Oh, shit. What do you got, Jeff? X to the 41st, y to the 15th, z to the 28th. Look how long that 4 is. Holy shit. That's the Slender Man 4 right there. Gotta watch out for Slender. So what I normally do is I kind of collect what comes out. Leaves myself a little space. 4 goes into 41 10 times with 1 left. 4 goes into 15 3 times with 3 left. 4 goes into 28. 7 times with?
No.
None left. Done. Yay, kick ass. X10, Y3, Z7, 4 through to this business. Oh, man. Some of you guys don't like that, but hopefully most of you guys realize that, and it's fantastic. Okay, that's enough. Ghosts and Slender Man and Matt. I like the Slender Man.